In this section, we're going to be talking about limits at infinity. Now, we had just discussed in the last section infinite limits, and this is something a little different. For, let's see, for an example, for infinite limits, which we talked about last time, we looked at something like this, where we have this function, and as x approaches 2, the function approaches infinity. The value of the function approaches infinity as we approach some specific x value here. That's not what we're talking about now. Now, what we're talking about is, shrink this up a little bit, is something like this. We're talking about a limit of a function, and let me write this here. The limit of a function, f of x, as x approaches plus or minus infinity. Right now, I'm going to just talk about infinity, which means that we're going this way. We're looking at what happens to the value of this function as x gets larger and larger and larger. Now, up until now, again, we've been looking at limits as x approaches some specific value of x here and talking about the value up and down. Here, we're talking about what happens to the behavior of the function f as x gets larger and larger, or in other cases where x goes towards negative infinity and goes to the left. So in this particular case, we can see graphically that as x gets larger and larger, it looks like the value, right, the up and down value, the y-axis, is approaching some number. I mean, it could go up, suddenly later, or down or something like that. But just from looking at this, it looks like as we get farther and farther to the right, it approaches a number. In other words, the value is not changing, or it's getting closer to some number. So let me show you on Desmos what this could look like. All right, so here's that same function. Let's look a little closer. So when we're around here, let's just start over here. We have a value of 4.9. I'm looking at the y value, the 4.9.41. And as x goes to the right, we see it's getting a little lower, right? 4.35, 3.767, and so on. And it keeps going and going. We have 3.345, but it's kind of leveling out, right? And let me move towards the right. If we go towards the right more, you can see what's happening to the value of the function, the y, the second number there, 3.145, 3.125. It's going down and down, but not rapidly, and it looks like it might be approaching the value 3. This is just an estimate, as are all of these graphic and numerical estimates of limits, but it looks like it's approaching 3. So let's look at this in an analytical way. In other words, let's look at the actual function and figure out what's happening. So this particular function that I drew in is the following function. 3x squared minus 3x plus 2 over x squared minus 4x plus 4. Okay. And if you can look at this graph, you can see where the asymptote comes from, the vertical asymptote at 2. If you put 2 in, you get 0 in the denominator, and we have, in this case, it approaches positive infinity for both the left and the right. But again, that's a limit, an infinite limit. Now we're talking about a limit at infinity. What happens as x approaches positive infinity? Okay. So what we do is we look as x gets larger and larger. In other words, if x is approaching infinity, that means the x value is getting larger and larger. You see in the numerator, well, x squared, whatever it is, that's going to get larger and larger. The minus 3x, that's going to get larger, but not at as fast a rate as the x squared, because whatever value is in there for x is going to be much larger. So this generally is approaching positive infinity in the numerator, but so is the denominator. And you may have seen methods of finding horizontal asymptotes using this way, but here we're going to be looking at and using limits, the idea of limits. So what we're going to do is, because we have infinity over infinity, that's basically what we're seeing. So for now, I'm seeing that this equals infinity in the numerator, the x gets larger, and infinity in the denominator. If this was a negative down here, like a negative x squared, this would approach negative infinity, and we'd have a positive over a negative, so it would be approaching negative something. But it still doesn't help us. It's indeterminate. Okay? So we have a method for this particular kind of function. And what we do is we look at the denominator, and we determine what the degree of this polynomial is. In other words, the highest degree is 2. So this polynomial denominator is a degree of a polynomial of degree 2. And so what we're going to do is we're going to divide every single term, top and bottom, by x squared. Remember, we're allowed to do that because this, in essence, is multiplying the top and the bottom by 1 over x squared. 1 over x squared. And then we, of course, distribute everywhere. Okay. All right. So that, as I said, that in essence, you're going to be dividing, or in effect, you're going to be dividing every single term, top and bottom, by x squared. We chose that again by the term of largest degree in the denominator, the degree of the polynomial. It doesn't matter what's here. If there's a 5x squared here, it's x squared that we're concerned about. It's the squared. Okay? So let me do that here. So this equals, let me give myself some more room. Limit as x approaches infinity. By the way, it's very important to, when you're writing these things down, and it does matter for exams, that when you're writing these things down, until you actually plug in numbers and find the number, the limit itself, you keep writing the limit as you're adjusting these things, because you have not taken the limit. So this limit equals this limit. When we actually plug the numbers in, then it will equal a number, hopefully. Okay, so I'm going to divide top and bottom. So we have 3x squared divided by x squared minus 3x over x squared plus 2 over x squared. That's the numerator. In the denominator, the same thing. X squared divided by x squared minus 4x divided by x squared plus 4 divided by x squared. And we then simplify. And I'm going to do it again. Limit as x approaches infinity. Well, this first term, the x squareds cancel out. We just have 3 minus the second one. One of the x's cancel out, and we have 3 over x. And the last one, nothing cancels out or simplifies, and we just have 2 over x squared. Then in the denominator, we do the same thing. And here we have 1 minus 4 over x plus 4 over x squared. So that's the final form that we're looking for here, the simplified form. This is the same function as we had here up above originally, just in a slightly different form. It is the same function though. Okay, so now the thing to know is, now we could separate with our rules of limits. We could say that this is the limit as x approaches infinity of 3 minus the limit as x approaches infinity of 3 over x, and so on, okay? And the top, and the same thing in the bottom, the limit as x approaches infinity of 1, and so on. I don't usually go through every single one of those steps. I'm going to look at the limit as each of these pieces and write down the result. The main thing to know here is that when we have any function that has a limit with an x in the numerator, or an x squared, or an x cubed, or anything like that, think about what happens here. Okay, so let me write this down. So in a simple case, limit as x approaches infinity of 1 over x. I'm just going to take some simple number where we have an x in the denominator. Well, as x gets larger, that means that the denominator gets larger. So we have, for example, 1 over 10, but it gets larger. 1 over 100, the x is getting larger. 1 over 1,000, and so on. We have 1 over, a huge number, 1,000,000. What's happening as x is getting larger? This number here, this expression, because the denominator is getting larger, the number is getting smaller and approaching 0. It doesn't get negative. It just gets smaller and smaller and smaller and approaches 0. It gets, no matter how big this gets. So as x approaches infinity, and as it gets large with no limit, and it just keeps going and going and going and getting larger, this is going to approach 0, always. So that's what we're going to have up here. That's how we're going to take care of this limit. we have everything in this term. So I'm going to look at, now I'm taking the limit, so I'm not actually going to write the limit. The limit of 3 as x approaches infinity is just 3. There's no x value to change anything. Minus, well, what happens here as x gets larger and larger, just like we said below, as this denominator gets larger and larger, this term here approaches 0. Minus 0. The same thing with this. As the denominator gets larger and larger and larger, this approaches 0. Over. And the same idea here. The limit as x approaches infinity of 1 is simply 1. Minus, and we have the same idea here. Because the denominator gets larger, this approaches 0, and this approaches 0. And we have 3 over 1, or 3. And that's our limit. Okay? And that agrees with what we kind of visually saw, that it looks like that's approaching, say, a single number. And when we looked at it in Desmos, you see that it looked like it was approaching 3. And there it is. So that's the basic idea. There are some a little bit more complicated things that you have to do sometimes mathematically. You'll have practice with that in homework and online. But that's the basic technique that we're going to use here. And that's what we're looking at. And basically what this does, like the infinite limits, it tells you about the behavior of the function. And here the function is approaching as the function approaches infinity, as x approaches infinity, we're approaching the value of the value of the function approaches a single number. In this case, it's 3. And so we have that behavior that we have like what we call a horizontal asymptote. It's not necessarily the same left and right. If you do x as x approaches negative infinity, you have to put in negative. Imagine what happens to your denominators as x gets larger and larger in the negative direction, larger and larger negative numbers. That's the basic idea, though. Practice these things in different forms, and you should, and also use the Desmos or a graphing calculator when you're practicing. You're not allowed to use these calculators on the tests, but to learn to get kind of the idea of it and to get the feel of it, they're great to use.